Hello, I'm going to be talking about polymers made from biomass. I'm going to explain what a polymer is, and then give some examples of different polymer feedstocks from biomass, and explain their applications as well as covering some advantages and disadvantages of using biomass over petrol. What do a non-stick frying pan, polyester fabric, cotton, and plastic bottles have in common? They're all made from polymers, but what actually is a polymer? Polymers are large macromolecules made up of small chemical units known as monomers. The majority of polymers are derived from petrochemicals, which are produced from refining petroleum. This process produces large amounts of toxic air pollutants, and the chemicals made then go into plastic production, which also has very high carbon emissions. To reduce these high emissions, scientists are developing ways to make polymers from renewable resources which have similar properties to current petroleum-based polymers. Polyethylene is usually derived from petrochemicals, but sugarcane can also be a feedstock. The sugarcane needs to be cleaned and processed to produce a juice product with a high concentration of glucose and a waste product called bagasse, which can be used to make paper or in hydrogel synthesis. The juice is then anaerobically fermented to give a highly concentrated ethanol, which is then dehydrated into ethene at a high temperature with an acid catalyst to be polymerized into polyethylene. The polymerization is exactly the same as petrochemically derived ethene and has the same properties. However, the process is a bit more expensive than making petrol polyethylene due to the price of bioethanol. There are two main forms of polyethylene, high density and low density. High density polyethylene has a linear structure, causing it to have a high density and more structural order, so it's more rigid and is usually used for containers, whereas low density polyethylene has a branch structure, making it have low density and less structural order, so it's more flexible, so it's mostly used for film and packaging. Both are strong and flexible with a good chemical resistance, and both can be recycled, but low density polyethylene is more difficult. The mechanism for this polymerization is a free radical mechanism. Usually a peroxide initiator, such as benzoyl peroxide, is used to produce a radical to attack the carbon-carbon double bond in ethene. The mechanism is an example of a chain growth mechanism, as each monomer is added one by one at the end of a growing polymer chain. The polymer length depends on the number of growing chains, and the molecular weight increases linearly as the polymerization goes on and the monomer is consumed. Corn and sugar beet can be used to make polylactic acid, which is the most promising biodegradable polymer available to replace petroleum-based plastics. They can be processed to produce hexose and pentose sugars, such as glucose, which are then fermented with a lactic acid bacteria to produce lactic acid. Polylactic acid is mainly synthesized two ways, by direct condensation polymerization or through a ring opening polymerization, where lactic acid is dimerized into lactide, which is polymerized with a metal-based catalyst into a polylactic acid. The condensation polymerization is an example of a step growth polymerization, as the monomers and growing chains have reactive alcohol groups, so all the species can react to make longer chains. Polylactic acid is used for packaging materials and containers due to its transparency and processability. It can also be used for some medical applications because it's biocompatible and biodegradable to manufacture tissues and sutures for dermatology and cosmetics. Cellulose can be used to form a variety of materials, and most of the polymers are biodegradable without adverse effects on the environment. It is a natural polymer found in plant cell walls and can be extracted from wood pulp and cotton. Cellulose films, such as cellophane, are produced by dissolving wood pulp in alkali to make viscose, which is then reconverted to make film, after it has been purified and bleached. The film is transparent, resistant to water, grease, and oils, and has a low permeability to gases, making it suitable for food packaging. Cellulose can also be used to make hydrogels, which have a high water absorption capacity and respond to temperatures, pH, and biological conditions, making them biocompatible materials that can be used to treat or replace any tissue or organ in the body. They can be synthesized by cross-linking cellulose chains together using other molecules. Cellulose nanofibrils could be used to replace PET as the flexible substrate in electronics manufacturing, as they have very high electrical breakdown tolerances of up to 1100 volts. Limonene extracted from orange peels can be converted into limonene oxide, which can be copolymerized with carbon dioxide to make polylimonene carbonate using a nucleophilic catalyst. The polylimonene carbonate mostly forms in the trans configuration, which is where the highest priority groups are on opposite planes of the ring. It was found to have a higher transparency and pencil hardness than BPA, which is a petroleum-based chemical usually used for coating applications, so limonene could potentially replace it. It can also be used to make films. These films are permeable to gas and have a high selectivity for carbon dioxide, so it's proposed to use these films for breathing glass, to remove carbon dioxide from houses and bring it into greenhouses. But with pressures of carbon dioxide being quite low, it was suggested it could be used in carbon capture technology to remove carbon dioxide from exhaust gases from combustion sites, so the carbon dioxide can be stored or utilised. There are many advantages of using renewable resources as feedstocks for polymers. The production of monomers produces less pollutants than petroleum-based monomers, while still being able to produce a versatile range of products, from having medical applications to being used in packaging. And some of the monomers, like ethene, can be polymerized with existing technologies, making them easy to synthesize. And of course, they are renewable, so the feedstocks can regenerate themselves and there's no fear of them running out. However, there are some disadvantages. The large-scale production of biopolymers is more expensive than making polymers from petrol, and although they are derived from natural materials and reduce greenhouse gas emissions, some polymers like polyethylene may contribute to plastic waste or break down into harmful chemicals. That brings us to the end of my video. Thank you for listening.